So we have reached the end of the road in terms of adding more chapters. We've started chapter 15. It is the last chapter that we'll be working on. So you had a recorded lecture yesterday covering sections 15.1 and 15.2, and I realized there was a lot of information crammed into that. But I'll show you in the examples today that most of what I covered yesterday in that video was just a repackaging of things that you already know and have already done. We're just introducing some new notation to try and make things more statistically rigorous. I guess that's the best way of phrasing this. And that means we have to formulate statistical hypotheses that get connected to how we do our data analysis. So the first part of that just has to do with formulating your hypotheses. And for the most part, since this is what we've worked with, hypotheses are typically going to involve either a population proportion or a population mean. And this is connected to, like, we know how to work with the sampling distribution of the sample proportion, and we know how to work with the sampling distribution of the sample mean. So if you have something dealing with a proportion, the relevant quantity is P. If you have something dealing with a mean or an average, the relevant quantity is mu. So I think that's a nice little guide. Like any problem you read that is hypothesis testing oriented, see if you can identify whether it's specifically asking about a proportion or a percentage. Then you're working with a P. Otherwise, you're looking at a mean or an average, and then the notation is mu. And so I have two examples here that try to illustrate the difference in what this looks like, and also how we then formulate those statistical hypotheses. So first one says, a snack company has found that 25% of their customers like date bars. They use that same recipe, design a prune bar, and they believe that a higher percentage of customers will prefer the prune bar. So to test this hypothesis, they do a randomized trial to determine what percentage of customers like the prune bar. And we want to state the null and the alternative hypotheses. So the null hypothesis is always the status quo, that which has been assumed to be true. And what is the status quo in this instance? Up to this point, the company knows that 25% of people like the product that they make. I know they're switching to a different product now, but the date bar is still the reference. That is the status quo. Also, with dealing with a percentage, right? You can see this quantity as a percentage. Later on, you have the word percentage. So percentage, proportion are the same idea. That means we're formulating a hypothesis around a population proportion. So you're always going to write H subscript 0 for the null hypothesis, then a colon, and now you need to make a specific equality statement about the quantity you've identified. In this case, it's a proportion, right? So our proportion has to be equal to the status quo. So our null hypothesis says this population proportion or this population percentage maintains the status quo. It is still equal to 25%. Then you're going to formulate your alternative. And an alternative hypothesis, again, I'll do a little sidebar here. An alternative hypothesis can either be a less than, a greater than, or a not equal to. you have to read for a clue as to which of those you should be working with. In this case, if you read the second sentence, it says they designed this prune bar and they believe that a higher percentage will prefer the prune bar. So the alternative says this proportion P, it is now higher than 25%. So you, in formulating the null and the alternative hypothesis, you have to identify whether it's a proportion or a mean that you're working with. You have to find what the status quo is, because that gives you your null hypothesis. And then you have to look, is there a direction for the alternative? These are the three things to ask yourself to help you formulate the null and the alternative hypotheses. But here it said state the null and alternate hypotheses, and there we have them. It's just those two statements. One of them is the parameter is equal to a specific value, and that specific value is the status quo. And the second one is the parameter, in this case, because the sentence said higher, our alternative says P is higher or greater than the 25%. Does anyone have a specific question about this first example? Okay, so let's look at the second one. The second one says the average reading speed for English first language or EFL persons in the US is 200 words per minute. A researcher develops a curriculum that targets both reading speed and comprehension, and they design an experiment to determine whether average reading speed is affected by the completion of the curriculum. State the null and alternative hypotheses. So, are you looking at a proportion or are you looking at a mean? Well, if you read it, the word average recurs over and over again, right? You're looking at average reading speed or mean reading speed. So the parameter of interest here is mu. So when you're formulating your null hypothesis, the null hypothesis has to say mu is equal to some specific value. And what is the status quo? What have we believed to be true up to when this researcher developed a new curriculum? Well, the status quo was 200 words per minute. So maintaining the status quo under the null hypothesis says the mean is equal to 200. Then what should our alternative look like? That's the next thing to establish. Is it going to be greater than, less than, or not equal to? Well, what does the researcher believe the curriculum does? Conceptually, the problem says it's targeting reading speed and comprehension. But if you look at what the researcher is designing the experiment to do, the experiment is just designed to determine if reading speed is affected by. It's not saying reading speed will increase. It's not saying reading speed will decrease. It will just say is affected by. So unless you have a specific directional word, increases, decreases, improves, something that gives you a direction, that's when you go to greater than or less than. If it's just saying is affected by or there is a potential change, then it's the very generic not equal to. So our null hypothesis says equal to 200. Our alternative hypothesis says not equal to 200. And there you have it. That's how we formulate null and alternative hypotheses. Now, when we start adding to this, when we start turning this into actual formal testing, there's a lot more that goes into it. But I tried to break down the steps here so that you can see all of these are concepts that we've covered and that you should be somewhat familiar with. So we're back to the snack company. They have a sample of 60 people who are trying this prune bar, and 17 people indicate liking the prune bar. Now we're going to follow some steps to test the null hypothesis. So first part, A says, write down the sampling distribution of the sample proportion. Calculate all related quantities, assuming the null hypothesis is true. So if I scroll back up, what did our null hypothesis say? The null hypothesis just said P is equal to 0.25. So if you see a statement that says, assuming the null hypothesis is true, that just means this is the reference value you're working with. You're assuming that the true value for P is equal to 0.25. So in that context, when we're talking about the sampling distribution of a sample proportion, that value has a mean, or the sampling distribution has a mean and it has a standard deviation. The mean of the sampling distribution of a sample proportion is always just the proportion itself. And the standard deviation for a sample proportion is square root of PQ over N. So in this case, square root of 0.25 times 0.75. And what is our sample size here? We're taking a sample of 60 people. So if we go and evaluate this, 0.25 times 0.75 divided by 60, and then I take square root, that gives me 0.056. Now, there's one last thing. Remember, if the sample size is large enough, then the sampling distribution will be approximately normal. And that holds in this case. You can go and check the specific conditions. But in this case, the sample size is large enough. So the sampling distribution is approximately normal with a mean of 0.25 and a standard deviation of 0.056. That's part A, and this is all stuff we covered in chapter 13, sampling distribution of the sample proportion. Next, we want to calculate the z-statistic associated with the sample proportion. So what is our sample proportion? That's notation is p hat, right? What did we observe? We observed 17 of 60 people liking the prune bar. I don't know who these people are, but they're out there. And so that is as a decimal 0.283. So that's just our sample proportion. Remember that our z-score is defined as p hat minus p divided by sigma of p hat. And that's just notation for the standard deviation. So this will be 0.283 minus the value of p is 0.25, and we've calculated our standard deviation as 0.056. So if we do this calculation, we get a z-score of 0.59. So there we have it. There's our z-statistic or our z-score. Now part C says, consider HA the alternative as specified in 1. And remember that our alternative said P is greater than 0.25. So what that the relevance of that is that tells you how you're shading your bell curve to figure out how to do your p-value calculation. So your bell curve has this z-score. Remember, the standard bell curve is always centered at 0. And now we've calculated this value, 0.59. And our alternative hypothesis said that p is greater than 0.25. The greater than here tells us we need to calculate the chance associated with the value to the right of our z-score. So that's the connection here. The direction in the alternative tells us which side of the z-score is important for the p-value. So this is our p-value. So to calculate the p-value, we're going to look up 0.59 in the z-table. In our standard normal table. So I'm flipping over to that. 0.59 gives me a probability or a chance of 0.722. Now remember, the normal table always gives you the value to the left. We need the value on the right-hand side. So our p-value is going to be 1 minus what we just looked up. So 1 minus 0.722 is 0.278, or 27.8%. We can go and express it as a percentage. So there's our p-value. Now, part D says state your decision with regards to the null hypothesis. Reaching a decision always requires a reference value. And so that'll typically be provided. I just want to talk you through that here. We're going to use 5% in this example. And what the 5% represents is we're saying anything that has a 5% chance or less of happening is too unlikely to just be attributable to chance. So if our p-value is less than 5%, we reject the null hypothesis. If our p-value is larger than 5%, we do not reject the null hypothesis. And in this case, our p-value, if we're comparing it to 5%, which is our reference, sometimes you'll also see that called the level of significance. Our p-value is greater than the reference value. So informally, the way you can say this to yourself is large p-value means large chance that H0 is true. And if the null hypothesis is true, do you want to reject it or not reject it? If it's true, you do not want to reject it. So you do not reject the null hypothesis. This is just a quirk of how we formulate our conclusions. We never say that we accept the null hypothesis. We either reject it or we do not reject it. That is the equivalent of, in a criminal proceeding, a defendant is either going to be found guilty or not guilty. They're never found innocent. So it's almost an exact parallel, our decision-making here, relative to how criminal proceedings reach conclusions, because we're weighing up the evidence. That's our sample data. and we're deciding, are we sticking with the null hypothesis, which is the presumption of innocence, or are we rejecting that in favor of the alternative? So what does it mean if we do not reject the null hypothesis? That's almost the trickiest part here, is stating your conclusion in the original context of the problem. So at the end of the day here, we were not able to reject the null hypothesis. You can say in the back of your head, but not write down, you're accepting the null hypothesis, which means the most likely outcome is that it's still 25% of customers who like this new prune bar. It's not greater than 25%. So we conclude that 25% of customers like the prune bar. That's the best conclusion we can reach. And often it's good adding just a little clause like saying, based on the sample evidence. So we're acknowledging this is based on data that we've collected, and we could be reaching a wrong decision, but based on all the evidence we've collected, that is the best decision we can reach. So I'm going to do one more example here. And I know there's a lot to take in with this. You'll see that even your homework for next week, for next Tuesday, is pretty light on, you're not going to have anything walking through all these steps, because I want to do more examples with you in another live session before I have you do some of these on your own. It'll mostly focus on formulating hypotheses and just basics of interpreting p-values, but not stringing all the steps together like in this example. So we are back to number 4, which looks at number 2, which is a randomized trial designed by a researcher, looks at reading scores. It is assumed that reading scores follow a normal distribution with a standard deviation of 50. The experiment, equivalently the sample, includes 25 people. So there's our sample size. And we were told our population has a standard deviation of 50. And our sample has an average reading speed. And I actually need to do a little fix here. It's not, I made a typo on here, and I just want to fix that. What's the easiest way of doing this? The average is actually not 270, it's 225. That's the average reading speed per minute. So this is our sample average. Our sample average is a reading speed of 225 words per minute. So just to refresh your memory from part 2, we had formulated our null hypothesis that said the mean is 200, and the alternative that said the mean is different or not equal to 200. Now, part A, write down the sampling distribution of the sample mean. So sample mean, if the population is normal or nearly normal, which we have in this case, then the sampling distribution will also be normal. And the mean of the sampling distribution, this comes from chapter 14, is just the same as the population mean, which we have under the null hypothesis. So that's 200. And the standard deviation is sigma over square root of n for the sample mean. So this would be 50 over square root of 25, which is equal to 10. So in other words, we have a normal distribution with a mean of 200 and a standard deviation of 10. Now we want to calculate the z-statistic associated with this. Now the z-statistic for the sampling distribution of a sample mean is y bar minus mu over the standard deviation of y bar. Again, that's just different notation here. So this would be our sample mean of 225 minus our mu value of 200 over our standard deviation of 10, and that will give you a z value of 2.5. Now part C says, consider your alternative hypothesis and shade the region that represents the p-value. Now here's my bell curve, centered at 0. I calculated a value of 2.5. What's important is if your alternative is two-sided, your p-value needs to be two-sided. So as big a step as you take from 0 to the calculated z-score, you need to take an equivalent step in the other direction. So we need to simultaneously calculate the chance associated with both sides of this bell curve. Now, because of symmetry, the two sides are equal to one another, right? Those two are equal. If we can just figure out one of them, we can double the value. So since the normal table gives us area to the left, will give us the chance to the left, if we go and look up the negative 2.5, that'll give us that left tail area. So here's my normal table, and I'm looking up negative 2.5. Second decimal is 0. So there's my value, 0.006. So my p-value is both tails in this case, and that's just a function of what my alternative looks like. So that's 2 times 0.006. So my p-value in this case is 0.012 or 1.2%. So part D again asks for a conclusion. Let's say we're using as a reference again the 5% level of significance. So we have to compare our p-value of 1.2% to 5% level of significance. And in this case, our p-value is smaller than the level of significance. So here we would have a small p-value, which means we only have a small chance that H0 is true. And if that chance is small, what that leads us to do is we reject the null hypothesis because it only has a small chance of being true. So then you'll see part E again asks for an interpretation in the context of the problem. Rejecting the null hypothesis means that our sample evidence suggests the mean is no longer 200 words per minute. Using this curriculum results in a change to the average reading speed. Now, your alternative was generic. It considered both sides of the Z table. So we can't just say that it has increased, even though our sample average is larger. The formal hypothesis test has to be consistent with how your alternative was written down. And the alternative just said is different from 200. So the conclusion that's appropriate and consistent with that says the mean is no longer 200 words per minute. Using the curriculum has likely changed the average reading speed. And we will definitely look some more of these examples next week. So again, this is not going to be leaned into very heavily in the homework. We will have more practice of this in class next week.